Okay, recording.
Okay. So since we should answer questions, I will start with the short comment on vortices. And in half an hour, I'll continue the main topic. Okay. Vortices. So when people say vortices, they mean originally that something is rotating. So this type of vortices were discovered many years ago in theoretical physics. When people study what happens with liquid, and under some condition, the laminar stream of liquid turned out into these vortices. And it turns out that the phase of liquid became the phase of full of these vortices, and that completely changed the behavior. Okay, people try to study this phenomenon, and after a long run, they decided that these vortices are best discovered, are best described in so-called Gaussian model. You may ask how Gauss, poor Gauss, is related to vortices. The answer is that Gauss is not related to vortices. Gauss is related to this type of integrals. No, it's great. The ability to take this integral is great. It's actually a scientific achievement of the 18th century. How vortices come out? Then people say that Gaussian model is a model that is quadratic in fields. What does that mean, model quadratic in fields? Action. You see, to be quadratic in fields, you need a notion of being quadratic. It means that you need a linear structure.
Right.
On target. Otherwise, the notion being quadratic is meaningless. So what has a linear structure on target? Natural R, but here we will not get vortices. R over Z. It also has a linear structure on target. That's why by Gaussian model, people understand sigma model with a target circle. So sometimes people call it free fields, but some people call it Gaussian model. So maps from sigma into S1 or product of several S1s. And it's clear that it's possible to study this model in any dimensions. What is great about this model is that this model has an important parameter, namely the action in dimension 2 could be written like this. So what this phi means? Phi is an angle on S1. So here is this model. And this model, study of this free model led to a lot of discoveries in theoretical physics. One of these discoveries was awarded by a Nobel Prize. Another, and the same discovery being rethought by Polyakov had enormous consequences, namely redefinition of what the quantum field theory is. And also it is a nice model, and it is a perfect model to study Siegel axioms. And also it's a model when you can give different definitions of conformal field theory. Great model, great model. So we have this model, and then let us see what are these vortices and why they play this specific role. I told you that in order to construct a local observable, you need to take a worldsheet, sigma, and cut out of it, in this case, a ball. What is remarkable? Remarkable is that when you are doing this, you are changing topology. Of sigma. And it means that potentially you have a new class of maps. When you are cutting out something, you generate pi1. So you have a new class of maps. And according to the general rules of quantum field theory, you have to add it in. Now, since the model is quadratic, you can not only speculate what will happen if you do it this way. You can make computations. And the basic rule of the Gaussian model is that this action is actually equal to e to the minus r squared s. Evaluated on classical solution times the determinant of Laplacian. And this determinant of Laplacian is the fluctuations around the classical solution. So you may ask, who keeps the topology of sigma? So this non-trivial topology is inside classical solutions. So these fluctuations have trivial topology. And they're the same. So once again, I made a mistake, prime minus 1/2. So they are here. Okay, so just imagine that you have this hole. Classical solution is of course harmonic. So phi classical is harmonic. How do you know it? From this action. So how to write down harmonic functions that correspond to a vortex, to the configuration when you wrap several times here? You do it as follows. You say that phi classical locally goes as log z minus a, z bar minus a, maybe with 1/2 here. Here you actually have a jump. Here you have jump of log. However, phi classical is defined modular integer jumps. So it is not a jump in solution. It is jump in coordinate description. So this is an allowed thing. Now it's interesting to compute the classical action. So S classical would go like this. Plus some other terms. And here you integrate z greater than r. So what is r? R is the radius of the worldsheet. Whole. So what do we have here? Here we have an interesting phenomenon. This thing goes as, okay, now I'll erase this classical picture. I'll erase this. And you would see that it goes like r squared log of r squared plus terms that are non-singular. When r small goes to 0.
So, Andrei,
Yep.
so it is still correct, right? That so this is a kind of a derivation from kind of classical equations of motion with a kind of the delta function, but it is on the other hand the same object as
no delta function.
Well,
no delta function.
Well, okay. Equations of motion outside the cutout disk.
Outside, yes, outside is.
But that's not what I'm trying to say. I'm trying to say that it's the same object as the product of left and right vertex operators with electric and magnetic numbers sitting on the lattice, which is prescribed by the target being a circle rather than line.
Here, I want to stress what is the definition and what is the accidental properties.
Mm-hmm.
Because let me say something. You see, at the moment, it's not about how to represent it, mm-hmm. how to represent an answer. At the moment is what actually happens, because it is, so it caused a lot of dispute in physics, this issue. Mm-hmm. So this is, once again, this is non-singular, and that's why we see that contribution of the vortex goes like this. Now, there was an issue. Should we include such configurations or not? It's a very important issue. So before I say, let us renormalize and do it like this, let us answer a physical question that was very important for physicists for some time. It means, okay, you have a hole. this thing is suppressed. So suppression is like this. Okay.
But
however,
this is
people say
this is fixed by modularity, for instance, that you have to include them.
it's another thing why you have to include them. You have to include them even before modularity. Because the reasoning that I have is important for not only for two-dimensional model. It's important for quantum field theory. This reasoning. People say. So the question is, should we include them or not? And there was an experiment and explanation by Polyakov. Experiment was done by Kosterlitz Stylus. Maybe they are written like this. Maybe, okay, excuse me, they got a Nobel Prize they don't care about. They were trying to put it on a lattice. And they were putting the theory on the lattice, the Gaussian model, and they wrote the following Lagrangian. Phi ij minus phi ij plus 1. They put here r squared. And here they put some parameter like r lattice. I think it went this way. So I don't remember this thing. Maybe it went upstairs. So in any way, it went like this. And they studied. So what was the idea? We need to write the periodic function. So cosine is 1 plus cosine of x. Is 1 plus x squared plus something else. Something else would be irrelevant. We don't care about it. That's how we do this derivative in the Gaussian model. So they put it on the lattice, and they found an interesting experimental result. When R was big, it was a conformal field theory. So they were happy. They modeled conformal field theory. However, when R came to R critical, there was a phase transition. The system behaved in a very different way. And it is called Kosterlitz-Stylus phase transition. And people studied it. They were trying to find what happened. And what actually happened was the following. They looked at the configuration and they found that small vortices become dominating.
But the point of phase transition doesn't depend on the spacing of the lattice. If it is very small.
It was independent on spacing of the lattice.
Independent.
Independent. Interesting. So it means that this phase transition has nothing to do with the lattice, because when R was big enough, you changed the spacing of the lattice, everything was smoothly. So what actually happened? So first explanation is like this. Since you have a lattice, you always have these vortices. Okay? Because there are holes. Now configuration of vortex of each particular vortex went like this. Okay? So each particular vortex was suppressed. However, there are many places where you can have this vortex. So there was so-called entropy factor. And entropy factor says that each particular vortex had suppression Each particular vortex had suppression like interesting r square to the minus r square. It was suppression of each particular vortex. However, in the square of length L, the number of vortices that could be was like L square over R square. So here we have a critical point. So when R square was bigger than 1, vortices were suppressed. When R square were less than 1, each particular vortex was suppressed, but probability that you will have vortex somewhere here was dominated by entropy factor. And we had this phase transition. You see, this phase transition, Stylus, produced a lot of confusion among physicists, because this phase transition was in contradiction with the R to 1 over R symmetry. So in the Gaussian model, you have exact mathematical answer, R 1 over R symmetry. In the Stylus model, you had this phase transition. So some young people started to argue, oh, T duality is violated, blah, blah, blah. So it was a trouble. Then Polyakov came to the game, okay? So poor great Polyakov, you see? So Polyakov, why Polyakov is poor? Because he is constantly suffering from misunderstanding and his not completeness of understanding of physics. That's why he is completely suffering from two sides, from external and from internal, you see? However, this constant suffering allows him to make discoveries. So what Polyakov discovered? He said, okay, this model, we don't know what this model is. I don't care about it. He came from my tap, where QCD was the main topic. And so he said, let us study analog of it, quantum electrodynamics. It has very similar action in the Euclid. And it has coupling constant. That is, of course, similar to this R, inverse of coupling constant. And there is the similar phenomena called electromagnetic duality. And everybody knows that this electromagnetic duality in dimension 3, so he studies three-dimensional theory, makes this three-dimensional theory equivalent, I'm sorry to say, but to the Gaussian model. Okay? So he studied this. And you see what he found. That because of U1, there is an analog of vortices here in this model. And vortex here. So if you try to, if you describe it on a lattice, you will have an interesting phenomenon. you are trying to describe it on a lattice using monodromies. So here we have this placket, and here we have monodromy. So you are trying to play with monodromies, since you want to keep gauge symmetry. And once again, you have similar phenomena, you have fluxes, and as a result, in your three-dimensional manifold, you will have not a vortex, but a line. So when here, in two-dimensional case, you have something that happens with the action, in the three-dimensional case, you start having particles. And these particles result to confinement. And once again, young and stupid people started to show, oh, Polyakov discovered confinement in U1 theory. I would say that you should not necessarily be old. It's much better to be young. But it doesn't matter. Either you are young or old, you should not be stupid. Okay?
Sorry, and they actually, I didn't understand this. What has changed when this transition to the 3D model happened? So first of all, it's U1.
Yes, it's U1.
3D. Okay.
And and we are studying three-dimensional things.
Yes. And what happens? So the change
and you have the same phenomena in one dimension higher.
So actually, what does it look like?
So I don't quite remember configuration, but so you may make a dimensional reduction, and you would see that it will be similar configuration. So
do you have square d-phi, star d-phi?
yes. So exactly. So
there's a typo, right?
So you mean here?
Yes.
It's a dual description.
We don't have a square. Yes.
Ah, yes, it's a typo. Yes, of course.
Yeah.
So what happened? What happened is that here you have a charged particle. In any case, you have a particle. The similar vortex description. But now you have these particles. So these particles are free, but you may check that they are charged. So I don't remember in which description he found these particles. But in any case, I remember that in one of the descriptions, they turned out to be charged. Particles. Like, Pasha, what you said in dimension 2, like delta function insertion.
Oh, I see.
And then people say, oh, you have charged particles. You have confinement.
Why?
And then there was a hype.
What does it have to do with confinement?
So if you have charged particles, and if you have two charges, then charged particles would screen. So in any case, you'll have screening in one phase that corresponds to confinement in another phase. So in any case, you have some strange behavior. Okay. You start to have charged particles out of nothing. And people say, oh, that's what happens. We have these charged particles. But Polyakov was wise enough Not to say that we are getting charged particles out of nothing. He just said, it is the problem of our description of a theory by putting action on the lattice.
Mhm.
You should not do it in a naive way. When you put it on a lattice, you will have a property that is orthogonal to the property that you would expect, considering it is a classical field and determinant. So lattice is not the same as Gaussian description. So it is actually a very strong hit on whom? First, it was a hit on Feynman. Why? Because when Feynman said, we have a path integral, he always assumed that we have a path. It means that we are putting things on the lattice. So if you put it on the lattice, you have something that you actually don't want to have. Second, whom it also hits. It hits the archive, all the hapless because people from the hap left assume for granted that you are putting QCD on the lattice, and it's okay. And it is a definition. However, if you apply this definition to electrodynamics in dimension 3 or to Gaussian model in dimension 2, you get unexpected properties. So this puts these computations, it puts question mark here. What are you computing? It also hits Millennium Prize. Because the Millennium Prize is about chromodynamics. And then the question is, what is the definition of chromodynamics? And people assume that definition of chromodynamics is what happens when you put it on a lattice. Okay? But when you start to put even a abelian theory on a lattice, you have something strange. So, this phenomena applied to gauge theories hits very important pillars of modern science. Now, you may think, come on, maybe our world is exactly like this. Maybe we are crazy and don't see this. That world is actually made out of lattice and not according to Gauss. Okay, Gauss has nothing to do with this description. Not according to treatment of Gaussian model. However, so people try to say maybe T-duality is wrong. Okay, maybe we were too naive. So it came from the young people. Okay, these voices. Okay, it's a hype, you publish a paper, T-duality is violated, etc.
So, Andrei, this kind of lattice experiment, it relies on a particular way to write down a lattice action with this cosine, but you could probably have written some other lattice
good.
action.
The point that Polyakov showed, that you cannot avoid it. Because Polyakov treated, he said, okay, forget about cosine. You may do something else. But still, if you have a lattice, you have the change of topology. Okay? You have the change of topology of the worldsheet from the very beginning. Because lattice has pi1 equal to infinity. A lot of holes. You cannot say that hole goes away. Previously, the hope that hole goes away was, if you have something that is moving around the hole, it is suppressed by kinetic energy. Yes, it is suppressed like this. But when you have too many holes, you have entropy factor. And the fact that you suppress each particular contribution does not mean that you suppress contribution in the finite size. So that's why it's good to be Polyakov, who suffers from internal and suffers from external. Of course, he suffered a lot while he was thinking about it, because it was complete contradiction. It was contradiction against the ideas of Feynman. And of course, you know that Polyakov is known for writing actions. For instantons, etc. Instantons have no meaning if you do not have action. Quantum field theory looks as having no meaning if you are writing action and putting it on a lattice. So it was kind of an existential crisis. Okay. So if you saw Polyakov, you can always see that he is suffering. So you can see constant internal pain on his face, even when he smiles. And it is because he was constantly thinking about such phenomena. So while other people are very happy getting money on computers, putting things on the lattice, you see, you are happy. If you are Polyakov, you will constantly suffer. And that's what he explained when he was getting the Pomeranchuk Prize at ITEP, from which he was expelled 20 years before. He was explaining that this prize does not help, but it cures a little bit his constant internal pain, because he actually suffers about quantum field theory, about physics, etc.
So, vortices always has effect in quantum field theory, and incidence is kind of particular vortices.
So he said that lattice that if you consider lattice this way, you probably can get something wrong. Of course, he explained this phenomena. He said that Gaussian model is a mathematical model. You have T-duality, and this T-duality is important for many properties. He just said that when you have lattice model, it is not the Lagrangian model. It is Lagrangian model plus operators with some unknown coefficients. And these operators are operators allowed by lattice definition. So you are not getting Lagrangian. You are getting Lagrangian plus everything that is allowed. And then he said, look, these guys have different conformal dimensions. Some conformal dimensions are greater than 2.
Sorry, Andrei, what you wrote there is cut off by the camera. So what is VI is what?
Okay, cut off of the camera.
Mm-hmm.
I'll rewrite it again. So he says that from the lattice, you are getting not just integral of the Lagrangian, but integral of Lagrangian plus TI's VI's, where VI's are what? Observables, allowed by lattice regularization. But then, he says, then you have to flow to the infrared. And if this thing is called irrelevant, it's his terminology after suffering with this. If VI is irrelevant, it means that conformal dimension of this is greater than 2. It will go to 0 in the infrared. That's why it's called irrelevant. So irrelevant, go to 0. If VI is relevant, then it would dominate. So if you go to the infrared, this would dominate. And it would change the theory completely. You do not want it in Lagrangian. You cannot do anything. It will dominate. And of course, between irrelevant and dominant or relevant, you have margin. Equals to 2. You have margin. And now let us reconsider Kosterlitz-Stylus experiment. When you write cosine phi minus phi, etc., you are keeping the symmetry phi 5 plus constant. You are keeping the symmetry. That's why you do not have operators of this form. Let me call them e to the I phi. Oh, I call it phi. Okay, fine. Times m. These are allowed. These have conformal dimensions that are n square over r square. You need to take into account that r is in front of Lagrangian. N is an integer. They are called momenta or tachyonic by historical reason. Observable. So when r is big, they, of course, have small conformal dimension. They are relevant. However, they are not generated because you have the symmetry. So if lattice preserves symmetry, these are not generated. Now, vortices have conformal dimension that is m square times r square. So this r came from the fact that it is in front of the action. That's why it has r squared. M means the number of wrappings. they are generated. But when R is bigger than 1, they are irrelevant. So what happens when you reach the critical R?
So what do you mean generated? What does it mean?
It is Polyakhov's idea that lattice is related to the Lagrangian theory in the following way. Polyakov breakthrough. That if you see what comes out of the lattice could be explained in terms of continuous theory by adding
yes, but by the infrared flow.
yes, by adding everything as the ultraviolet that is not prohibited by symmetry. So tachyons are prohibited by symmetry. Okay, vortices are not, but for R greater than 1, they are irrelevant. When R comes to this place, to 1, there is a phase transition. Irrelevant become marginal and then relevant. It is exactly the Kosterlitz-Stylus phase transition with the, I would say, with Polyakov's explanation. And then, of course, with this lattice regularization, you are always in this phase. Now, if you have a dual description, okay?
So I missed something that you said about the tachyons. So you said that they are prohibited in which sense?
They're prohibited. These guys are prohibited because if you make the symmetry phi plus c is a constant, not an integer. They are not invariant.
For C arbitrary, yeah.
Yes, for arbitrary C. However, when you have cosine, it is of course a symmetry. When you have d phi, it is of course a symmetry. But it's not a symmetry of these. So there are such things, but they are not generated. So Polyakov says, you see, Polyakov helped. So actually, Polyakov helped Feynman. So when it was complete destruction of Feynman's idea, Polyakov said, no, we still can use Feynman in this interpretation. Okay? So vortices at Kosterlitz-Stylus, so that's what happens. And that means that when you are saying that you are writing down functional integral, you should give a definition. What are you meaning by functional integral? So hand waving, saying that everybody knows that of course we assume that we put it on the lattice, and when lattice goes to 0, it's exactly what we want. This is wrong. In general, there are phenomena that you have to study and to show that there is no Kosterlitz-Stylus Polyakov phenomenon. So I'll put him the third. So these guys discover and he interpreted. Okay? Together with Polyakov, together with the Polyakov fake confinement. So Polyakov is not stupid. He said that if you try to approach abelian theory in 3 dimensions from the lattice, you will get confinement that you actually don't have in abelian theory. It breaks everything. It's not to say that there is a confinement or charged particles from nothing in abelian theory. He is not stupid, you see. Abelian theory is around us. Okay? So in dimension 4, we'll have some kind of strings floating around us. We don't see. It means that we need to think in some details. What is the definition of quantum field theory? So here, Polyakov is a person who strongly thinks about it. And that's why, after some thinking, he went to the idea that quantum field theory is not action on a lattice. You see, he discovered it because he studied it. He had a pain. He suffered. Is a critical phenomenon. So you put something like spins on the lattice, and you see something very different in continuum limit. And sometimes you can have no Lagrangian. So he got this idea after years of suffering. And nowadays, when people, you see young people that are not properly educated, are opening the books, say open the book of Polyakov, when he says that quantum field theory is a critical phenomenon, etc., they don't even understand that Polyakov, of course, was thinking about putting action on a lattice, and he found phenomena that made him to go away from this definition. You see? By the way, this mistake was done not only by young people. The most striking example of this mistake is done by, so do you know the name that I would like to pronounce with a tremor? Who is the person who made this mistake in the most ridiculous way, in the most how to say, in the most important set of lectures? Okay, so it's a guess. Try to guess.
Buratino.
Who is it? What?
Buratino.
Sounds close to Buratino, but not Buratino. The name is shorter. Who is this remarkable scientist who demonstrated to the full world, and especially to mathematicians, that he is not understanding quantum field theory? Sounds close to Buratino, but shorter. And it's a person whom I respect very much, but you see, if you are great physicist, it means that you are making great mistakes, okay? So who is that great physicist? And where were these lectures held? Okay. Who is the great physicist? Where these lectures held?
It's like a pop quiz.
As I say, in front of mathematicians, in front of most respectful mathematicians.
That's Edward Witten. Yeah.
Sam, good. Edward Witten. Now,
IS.
what is the place?
IS.
Of course, Princeton.
Yes, I was there.
Okay, so you see, Sam, it's because you are from Princeton, yes, and
Yes.
and he started the lectures on quantum field theory, and first he explained it in terms of lattice regularization, because he understood that you cannot say to mathematicians some hand waving. They knew that it was very hard to define analysis. They knew, so what mathematicians knew? No, they are not stupid, they were Deligne, Pierre Deligne, the student of Grothendieck, and many other great mathematicians. They knew that mathematicians, in order to define this, okay, they had to develop epsilon delta language. That and everybody is suffering in universities because they want to define what the derivative is. Okay? While for Newton it was obvious. It's epsilon delta language. Also, length of a curve. It is something that is obvious for everybody who has any kind of curve. Okay, you see, I'm trying to get a curve. Unfortunately, I don't have any curves. Maybe this. Okay, this is a curve. It is clear that it has a length because it's the length of a wire. But if you want to define the length of a curve, you need to be very accurate. How you make it from an interval. A lot of work. Okay? And for these people, you cannot say, just take an infinite dimensional integral, because they know that even in the finite dimension, it is a work to make it mathematics. And therefore, Edward Witten started with the lattice things. And of course, he knew physics a bit, and he said about the Kosterlitz-Stylus phenomenon. Great. So I don't remember if he said that we need to exclude this phenomenon. But then he continued with his lectures. And when he continued, he was speaking about what? So, okay, first part, I don't remember, first semester. He was talking about lattice and, of course, Kosterlitz-Stylus phenomena in Polyakhov's interpretation. During the second semester, he was talking about supersymmetric theories. And U1 effective quantum field theory. And somehow showed, unfortunately, that he is not understanding what quantum field theory is. Because from his first semester, he should know that there is Kosterlitz-Stylus phenomena, and this phenomena is dangerous, especially for U1 theory. In the second semester, he was talking about supersymmetric theories that are defined by writing Lagrangians. Without saying how do we put it on lattice, and why high SUSY is not broken by lattice. And second, he said nothing about Kosterlitz-Stylus Polyakov phenomena in U1 series. So, okay, you know that in Russia we have a Jewish joke. Then two Jews were quarreling, as Jews always do, and they came to a rabbi. So actually there was not just two Jews, but three Jews. Two were discussing something, and third that took them to Rabbi. And then Rabbi said, look, you are right, and you are right, and you, the third one, who says that they could not be right simultaneously, are also right. Okay? So it is an old Jewish joke. However, what Witten did was just the illustration of this joke. In the first semester, he explained the lattice approach. In the second semester, he explained the Lagrangian approach. From his lectures, it was clear that they are incompatible, and especially incompatible in U1 series. But he still put it in the same course, okay? And now it turns out that who are fools here? So fools here are, of course, great mathematicians. Because when you explain something, it's very easy for you to make a mistake. But mathematicians, especially those from the Grothendieck school, know that, okay, if you are from Bourbaki school, you know, you know that when somebody explains something, you should be able to catch him, to catch contradiction. And there was also a well-known test. So when Bourbaki started, they put their colleagues to the test. And the test went as follows. They wanted to test Mr. X. Oh, he was not Mr. It was in France, so he was a Monsieur. So they wanted to test Monsieur X. So they made a plot. This is the days when we test Monsieur X. And then the speaker started saying some nonsense. Not complete nonsense, but he is trying to give wrong proofs. Proofs that look close to regular, but wrong proofs. He intentionally was making mistakes. And everybody besides Monsieur X knew that. And they kept quiet. And Monsieur X had to stand and say, come on, it's nonsense. It's wrong. So somebody from Bourbaki made this test, and when they started running their seminar, people were tested. So it was in good old 50s. Nowadays, in 90s, the followers from Bourbaki were hearing all this, and it passed through their mind. So I would say that these great mathematicians all together failed the Bourbaki test. They had to catch Witten and say, no, first semester is incompatible with the second semester. What are you talking? No, they were sitting with open mouth, making computations, making exercises, not being able to see that first semester contradicts to the second semester. And so nowadays you need to pay $100 to get this Witten's lectures, because now they put it, now they're charging for downloading it. By the way, they never tried to write down Waffer's notes because they considered it's too hand waving. So Wafa is great. Wafa is great, but he is incompatible with mathematicians. So he gives the results, and they are proving his results as theorems. Like 10 of Wafa conjectures. They are proving it. They are getting awards and positions for proving Wafa's conjectures. But they just cannot follow Wafa's arguments. Because in each particular step, Wafa's arguments are wrong. However, the result is correct. And they cannot understand how a person who is doing mistakes constantly gets a correct result. Because Wafa has a great intuition, you see. But they cannot make his notes. Written is better. So he wanted to give some message. But if you read it like this, it's a complete contradiction. By the way, this first semester, he borrowed from Polyakov. It's not his. Second semester, it's completely his, together with Zyberg, of course. Second semester was written Zyberg. So altogether, it's incoherent. So it is published. And when poor mathematicians will try to study what quantum field theory is from these notes, they will be completely lost. Because they see great Edward Witten Fields Prize. People in the audience, several got Fields Prizes. So they expect to be great mathematicians. And he is expected to be great physicists. And he explained to them, first semester, second semester, they don't see anything strange. So poor young mathematicians will think, no, I am completely crazy, you see. I am stupid, I have to leave my job. I have to go to C++ programming. Because I cannot understand how it could be. And he thinks that it is his problem. No, it's not his problem. It's a problem in our society. And that's why I'm stressing this important point. Okay? So you see, this story of what vortices are led to this, if you start to think, led to all of this. And when Pasha says, it's like this, you write chiral vertex operator, you just write e to the I phi left plus vortex, okay, how you call it, phi left, n plus nr plus m over r, and this phi left is the left mover, etc. No, it's not enough. When you write it this way, you are hiding what's called physics that is behind it. And some people say that I'm a mathematician, not a physicist. So they are wrong. At least I share the suffering that physicists have. Okay? So here I suffer together. I suffer together with Polyakov. I suffer together with Witten. You see? And I'm telling you some piece of their suffering. And this is a nice cover. Pasha?
Yes.
Do you see what I mean?
No, I'm thinking. So, well, okay. So you explained the following, that, well, there is a latest proposal for a replacement for the compactified free boson CFT, which has a phenomenon which doesn't occur in free boson CFT, which doesn't occur when you try to take the lattice space into zero. And well, this contradicts our intuition that the one model should converge to the other, and that's good. So that one model has a phase transition, the other doesn't. But I don't understand where in the story, fits this three-dimensional QED with values in U1 because that one was not a lattice model?
Because when you try to do three-dimensional QED, you would like to write three-dimensional QED with a compact gauge group.
That's fine, but that's a continuum model. So what you are teaching us that there are incurable lattice artifacts, but then as a model for an incurable lattice artifact, you gave us something that is not a lattice theory.
No. Of course, so maybe you would like to see the model. So if you'd like to write down the model, you can go to the Edward Witten's lectures where he follows Polyakov. So there are several ways to say it. So the question is, how are you doing lattice gauge theory? Some people say lattice gauge theory is done out of monodromies. So this is a placket. So you try to understand what the gauge field is. You have a group element. Or actually, if you want to have the same orientation, you would like to say that there is a Wilson line, parallel transport around the placket. That is G1, G2. Here we go oppositely. G3 minus 1, G4 minus 1. Okay? So this is a group element. Okay? And people say, okay, degrees of freedom are not connections. Come on. Degrees of freedom are monodromies. You put monodromies here. So this is a group element. And then you would like to understand what is the curvature. So you are trying to write G as e to the a with small spacing epsilon. And of course, for a abelian group, you can write down a curvature. If you write this thing down, what would you get? Of course, you will get a curvature. Okay? So it will start with 1 plus epsilon, and then you will say something like
it's invisible, and it's cut off by the camera.
Okay. You see, cutoff are always dangerous. Okay. Okay. So here is G, the monodromy. The monodromy U is so here is the point X, Y. I will write it in 2 dimensions. Here is X plus delta X, Y, right? Here is X, Y plus delta Y. Here is X plus delta X, Y plus delta Y. Okay? What monodromy is? Something like e to the a y at x. Okay? E to the a x at y plus delta y. Here. E to the minus a y x plus delta x. E to the minus a y. Okay?
Mm-hmm.
And then you expand. And then you expand, and of course, you see that it is, of course, 1 plus what? Plus, okay, or minus. So here will be minus dx ay. And from here we will get, of course, dy ax with a plus. So this would go like 1 minus, of course, delta x, delta y, curvature xy. So there is a way to write down this placket action in terms of monodromies. And you would say, hooray, I put everything on the lattice. The gauge groups, of course, are gauges, are gauge transformations that are sitting here. So in this way, you get a lattice action.
Oh, you're saying this because you're saying that this Polyakov's three-dimensional U1 QED should be transformed in this way. Put on
Yes,
the
of course.
Okay.
Yes. Well, yes, it's one of the ways to say it. You can do it this way. You can do it in the opposite way. But inevitably, you will have this phenomena that the lattice, once again, lattice is full of holes. Okay?
But this phenomenon that you say that he observed, this phenomenon of confinement or screening of charges or whatever it is, this is about discretization, or is it not?
It is because of discretization, of course.
Mm-hmm.
So when you make discretization, you are getting this phenomena back.
Mm-hmm.
So you have artificial vortex lines. You have many vortex lines. So these vortex lines are like charged particles that are in the vacuum, you see. You have to add them and they break the phenomenon.
Mm-hmm.
Once again, it is not enough to have the small spacing. You need to have a small charge, okay? But once again, E square 1 over E square is the S duality. And Edward Witten is famous for S duality explanations. Also, E square 1 over E square is the basic tool in effective U1 theory. So you need to estimate the irony of all this. So what is Seiberg-Witten theory about? It's about that you have 4D super young mills, n equals 2, and you study low energy theory. That is a theory that is described by elliptic vibration. And the basic tool, why you have elliptic vibration and all this, is abelian electromagnetic duality. All the theory is about electromagnetic duality. However, it is this phenomena, if you put it on the lattice, that breaks electromagnetic duality. So that's why, would I be Edward Witten, I would either speak about Kosterlitz, Stylus, Polyakov, or about n equals 2 super young means. I would not speak about both. So if I, being Edward Witten, understand that these 2 points of view are contradicting, I will wait several years or decades until they will come together in my mind. So I will choose one of the topics. Either Kosterlitz, Stylus, Polyakov, and I will explain that quantum field theory has no Lagrangian, it is a phase transition and all that. Or I would explain my own great result about super young meals and low energy U1 theory. But I would not explain both, you see? Or even if I'll explain both, I will give a lecture in the beginning or at the end that quantum field theory is far from being complete. We have great results of Kosterlitz, Stylus, Polyakov type. And we have great results of Edward Witten and Zyberg type. We have both results in quantum field theory, but we have no idea how to relate them. And this is an open problem. But he took neither first nor the second path. And maybe that's why Edward Witten is really great. So I just cannot understand why he, having this understanding, has chosen such a way of describing things to mathematicians.
So can we use BV on lattice to explain?
No.
No.
No, you see, we cannot use BV because in BV we strongly go with Lagrangians. In Kosterlitz, Stylus, Polyakov, we say quantum field theory is phase transition. And in order to describe Lagrangian, we need to show a system that looks as continuous field. And nobody was able to make a 4-dimensional lattice model that would have critical behavior as 4-dimensional super young meals. So the only people who did it properly are people who are doing 2-dimensional integrable systems. So sigma models, okay.
But for Polyakov is 3-dimensional, it's not a 4-dimensional.
Yes, but in 4-dimensional you have even stronger phenomena. For 4-dimensional, you will have artificial strings. That is even worse. So what people know, as far as I know, in dimension 2, there is CPN models. That have both descriptions in terms of Lagrangian and also in terms of lattice. So it is a result of very hard work here and here. And it seems, now it seems, that these two approaches coincide. But this is in 2 dimensions. Nothing like this is known in dimension 4. So for dimension 2, you can run out lattice model, you can run many things. So what is the proper lattice definition? In D equals 4, nobody knows. So maybe there is something, but at least I don't know. Sorry, when I say nobody knows, I say I do not know. So when you ask me, what is non-perturbative, four-dimensional, interacting theory, I would say, actually speaking, I don't know. What I know free theory. What I also know is what I talking about, instantonic theory.
How about 3 dimension in lattice, over lattice?
I don't know. I don't think there are no. But you see, here I have free theory, instantonic theory, where we still have to sum over instantons. It's still summation, and you need to also perturb it, because it's in a special region on the space of coupling. So I understand this. I understand this. Of course, I understand classical theory.
I'm sorry, can I pinpoint something interesting?
Yes.
When you are working in different dimensions, you may have a different lattices in terms of their groups of shifts. So how they coincide when you take different lattices with different groups, maybe in the limit or
Nobody knows. It's a good point. It's a good point that lattice violates Lorentz. Very good point. So lattice violate Lorentz. I forget how to write this Lorentz. Let it be this Lorentz. Pasha, what is the proper Lorentz? I am always forgetting which Lorentz is which.
I think this is correct.
Or this Lorentz.
I think this is this Lorentz, yes.
So you see here, you have this symmetry and this symmetry. No rotation. You say that rotation is restored in the continuum limit. However, continuum limit is something that has to be proven. You see, in old mathematics, there was a problem of the length of the circle. Okay? Because you can have different approximations.
It's not just Lorentz. I mean, we started with the example which was a CFT, and of course, the lattice is not compatible with conformal transformations.
Yeah, but it's also not even compatible with Lorentz.
Yeah.
And you see, when you speak about supersymmetry, things become even worse, because supersymmetry is a symmetry that is, you see, you have some odd symmetries. You need to guarantee that odd symmetries are there. You see, once again, there was an old problem about how to define the length of the circle. You can have this polygon. You take the sum of intervals, and then you cut it into two. And then you cut into two again. And in the limit, you think you will get the length of the circle. But you can make some other procedure. And you had to prove that all these procedures give you what everybody knows. Take a circle, there is a length. So you feel that there is a length, but you don't know how to define it mathematically. By the way, there are contradictions here. So let me show you the fake definition. Suppose we have a diagonal, okay? Let us approximate diagonal with a staircase, okay? You see, this staircase goes to diagonal. However, the length here is always 2. It has nothing to do with the square root of 2. Okay? So it's an old puzzle. The length of the staircase is. So you need to understand what does it mean to approximate something with something. So when you approximate lattice, when you approximate space with the lattice, potentially you can have many problems. And the Kosterlitz, Stylus, Polyakov found just one of the problems. So the main thing is that we do not have definition. And when physicists were working, they saying, okay, we do not have definition, but we feel what is the right thing to do. They say that physics is like an art. When you feel that it should go this way or it should go that way, and they are arguing, it is because of the physical common sense. Okay? I completely disagree. So, all problems in physics should be determined not by some mysterious physical sense or mysterious wisdom of physics. All phenomena should have everything should be given a definition, and we can try to prove something using definition, and otherwise we'll always be in trouble. And it is worth to pay to people who are working hard on definitions. Like in the 19th century, it would be worth to pay to people who are doing this epsilon delta, okay? So it is worth to pay to people who are studying definition of, say, what is quantum field theory, what is functional integral or whatever, what is lattice, how to go from lattice to continuum. Of course, lattice has a lot of problems. You see, it's lattice has holes. Lattice breaks invariance. Lattice breaks this. Lattice breaks that. Okay? However, functional integral also has problems. So everything has problems. We need to spend some time on understanding what is going on. You see, people would agree to spend some time either if they are crazy like Polyakov, who decided to devote his only life on thinking, on hard thinking on it, or you need to pay them to do this research, okay? So it is like with medicine. You can either have crazy doctors who are agree to drink the urine of their patients. You know, it's a person who discovered diabetes, that diabetes is related to sugar. He was drinking the urine of his patients, okay? So nobody now among doctors would like to drink urine of their patients, right? Okay, so now doctors are paid and we go somehow, okay? So nobody will spend his life like Polyakov to find all this phenomena and suffer. Okay, so we have to do it in the regular way, like doctors, okay?
Yes,
There are a lot of problems. By the way, Stas Smirnov was given, as far as I understand, a Fields Prize for works on percolation, where he basically proved that on some approximation you get exactly what you expect. Okay? But he proved it.
Yes, thank you.
Okay, so this is now we need to make a break, okay? because I was talking for, instead of 30 minutes, I was talking for 1 hour 40 minutes. Okay. But I think I explained something important.
Thank you.
So, and then after 5 minutes break, I'll explain you what I plan to explain, namely the tropical particle and tropical Feynman diagrams. Okay, so now we will have 5 minutes break. Okay.
Okay.
So Pasha,
I'm sorry for derailing you. Yeah.
no, it's good to derail, but you need to follow advice of your father to keep me by button. At least, but I explained something important.
Oh, I should have said that I'm going to ask you a question, but I expect a one-sentence answer.
Okay, please. Okay. Okay. Okay.
But no limit on the amount of words in the sentence.
Okay, so now break. Okay,
Right.
break.
Yes. No, but Andrei.
Yes.
So, well, metaphor. So, if we are sort of saying that, we are replacing, I don't know, a space with a lattice, and we are upset that pi1 appears. It's like replacing it with a cell complex and being upset that the first skeleton has a pi1. Well, in topology, there's a very easy cure: just adjoin the remaining cells. And then it has the correct homotopy type.
Okay.
Well, I don't know how to translate it back into field theory.
By the way, very good idea. So you have to invent something that kills this thing. Oh, so you will not get a Nobel Prize for this. You will not get a Fields Prize for this, but you can cure something.
All right. So
maybe, but yes. So space. So okay. So space would be a model.
So the role of higher cells is to kill the
yes, right,
to kill
right.
the cycle. So if you can kill the vortices,
yes, kill the mockingbird. Okay. Kill the vortices. Yes. Like in Borges, yes. It's called the Raganyok, as far as I remember. When they came to hear about, do you remember this?
No.
Short story. Raganyok, Jorge Luis Borges, or Гибель богов, so death of gods.
Ragnarok,
yes. So it's a great 3 pages that I admire very much. The more I am thinking about it, the more I admire Borges. Okay. So can I admire somebody? Okay. I admire many people. Actually, I love people. I love people when they make progress. I love people when they are guessing things. I also love people when they are making mistakes. They are people. It's normal. It's normal.
So are you saying Wafa was also part of that semester in Princeton, for which this 2-volume book?
Yes, great Wafa. Once again, great and ununderstandable Wafa.
And his lectures were just never, sort of, the notes never
Never
appeared?
And there was no video, so we don't know what he was talking about. You see, you should not make Italian soldiers, okay? They are very interesting people, but you should not make soldiers out of them. You should not make mathematician out of Wafa, okay? So people are different. So you should consider what Wafa says as an insight from God. Okay. Just take it. Waffe is great. He has enormously great intuition, and he is unable to explain why he's thinking this way.
Mm-hmm.
So can somebody be great? Yes. Gift.
So, Pavel. Hi.
Hi.
Yes. Hi. So, you wrote some very interesting papers on quantum field theory with boundaries.
Right. Yeah, so
Yeah.
there's this program for.
PV.
Mhm.
Yes. PFV with boundaries. Yeah.
No, thank you. So the whole program that was going for a few years with Alberto Catania and Colli Reshetich, but now a few more co-authors with
Hi.
yeah, like it's the idea is to start with BV, but also to mix it with sort of functoriality in field theory, functoriality in the sense of Siegel. So to be able to glue and cut. Oh, Siegel and more ambitiously with like Luri, so cut with corners.
Yes.
But for that, I guess that requires some, that we maybe understand in some examples, but yeah.
Yes, I think that gives a nice framework But to go further, we need to study this renominations and renomination group.
Absolutely, yes. Absolutely, yes.
Yes. Yeah, so we are interested in some examples in 2+1 dimension.
2+1. Mm-hmm.
2+1 dimension, yes.
Yeah. So, yeah. So we thought about like a very baby example of it is actually with even without BV, but with gluing and cutting, but sort of renormalization with gluing and cutting in 2 dimensions, but sort of on surfaces. So they're the only thing to sort of deal with is well, scalar field theory with the potential and with sort of TET poles and how the TET poles are glued and cut, and there's already some sort of interesting story there.
Mm-hmm.
But it should be much more substantial in 2+1, as you say. So which model in 2+1?
So I came back, but before I'll continue, I would like to say that I like your idea. So people are talking about counter terms, and you are talking about counter topology. Okay.
Mm-hmm.
So it means that from the very beginning, we should assume that there are these counter phenomena.
Mm-hmm.
And it seems that they start from dimension 2. That's interesting.
Mm-hmm.
Mm.
Yes.
And that's because in dimension 2, the whole produces topology. In dimension 1, the whole is nothing, basically.
Mm.
Okay, so the rest of the audience, in any way, it is a virtual audience, okay? And the rest of the audience would, so what should we do? We should make a comment with this video that the first piece, that the 2/3 of the discussion was about general problem of quantum field theory. So we should have post description of what happens, okay, of what happened. Then it would be possible to trace. So now let me come to what I wanted to discuss. By the way, I heard that Gelfand seminar also went this way. There was a starting point, and when people started to discuss, they typically deviate from the topic.
Mm-hmm.
They came to the topic at the end. So, and I saw the same at Greenfield seminar in Chicago. So you would have a starting point, okay? And then we go somewhere. But still we need to discuss what was planned at the very end. Okay.
Mm-hmm.
I think it's okay. Pasha, what do you think?
No, absolutely. I'm very excited. So you wanted to tell us about connection to BCOV and tropical curves.
No, yes. So now I want to tell you how to use so what I was talking yesterday. So yesterday, so let me give a brief reminder. I was telling you that, okay, I need to bring the blue pen back because blue is for the compactification devices. That curves are like this. So this is tropical CP1 times CP1. Okay, no, I cannot write it right with this. So it is a curve in CP1 times CP1. When there are curves, so can you see at least a little bit of blue? Pasha?
A little bit, yeah. No, it's visible, it's faint.
Okay. So I explained that these are curves. And I also explained that actually the curve has not only a direction, that the curve is associated to the integer vector that points into this direction. So my example was, okay, quadratic equation. Almost quadratic equation. So this is thick, this is thin. Okay. I will call it animal diagram. Okay. This animal diagram is for y equal to x minus a, x minus b, x minus c squared. Okay. So you may think of this line as a zero. You may think of this line as an infinity. Here is a, here is b. So for small x, we are here. So it's something like a plus b minus c. For big X, we are here, it's like 1. And here is C. Dot, 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 dot. This is C. This is C. So when X hits C, we go to infinity. And then we constantly go to 1. Now, this line is vertical and has a vector 0, 1. This line is vertical and has a vector 0, 1. This line is horizontal, has a vector 1, 0. This line is diagonal 1, 1. This line is 1, 2. So the vertical vector and diagonal vector join together into vector 1, 2. I'm sorry. Now, this line is a vector 1, 0. It's horizontal. And here, of course, we have the vector that is 0, 2. So 0, 2 is a vector corresponding to the second order pole.
So is it correct that these arrows, they don't really mean anything? The arrows.
They mean the arrows. They mean the direction. Because when you are moving this way, you are wrapping the face in some direction. In order to explain this, let me make the following remark. Let us study what does it mean to have a map C star to C star. Holomorphic map. F, this map is y equals to what? To z to the power m. In logarithmic coordinates, log y equals to what? M times log z. Here we have this m. Actually, here we can put a constant, and then we can have this shift. So here, we can distinguish +1 is not -1, right? So on each of these C star, you can have an orientation. Let me put it in this marks. Orientation of C star. Of course, it's a tropical orientation, okay? Because C star is a complex manifold. It of course has orientation as a two-dimensional manifold. However, on C star, we have, so C star being a S1 times R, we may choose orientation on this R. Okay? So we may say that everything is oriented. Pasha, do you see what I mean? C star contains R separately from S1.
Yes.
We can orient this R.
Okay.
And so when we have holomorphic maps here, yes? It's better to write them down somehow. Here we choose orientation of the real part. Here we choose orientation of the real part. And the map is linear. Here we ask how we change one orientation, how orientation here and here are related.
I see.
And it is interesting to note that if you change orientation here and here, you will get the same map. All right? So when you have an image, okay, you may put orientation on the source and on the target. Okay? So when I'm writing here these things, I mean here there's the source. So here I am already thinking in terms of the parameterization of the worldsheet. So before I put these vectors, okay? Before I put these vectors, you may think of it as an image of the curve in CP1 times CP1. But if I'd like to think about it as a map of parameterized spaces, I need to put vectors everywhere. Okay?
Okay.
So now, you see, by the way, you see that when C goes to infinity, it's quadratic equation. C is going to infinity. So you see, I like to illustrate everything on examples of quadratic equation, okay? It is kind of a challenge. Illustrate all notion in mathematics in terms of quadratic
So,
equation.
sorry, I didn't understand what you said.
Consider this curve.
Yes,
When c goes to infinity,
yes.
and I renormalize, it's a quadratic equation.
I don't understand what you said.
Y equals x minus a times x minus b.
That's not c equals to infinity. Sorry.
Okay. When I write it this way,
Okay.
you agree that it's quadratic equation?
This, yes.
Yes. Now let us compactify it somehow.
Mm-hmm.
It's much better to compactify, to see this as a map of projective spaces, not as a map from the line to a line, but as a map of a line that has these things here, to a line that also has these things here. What we know?
Oh, two things are one thing. It's sorry, it's from CP1 to CP1.
Yes, from CP1 to CP1.
Yes.
So this is something that was introduced by whom? When projective geometry was discovered, I forgot his name. Pasha, could you help me? So
I don't know, Desargues, or I don't know.
Desargues, of course, Desargues. So Desargues was saying, we should add infinities everywhere. Please add infinities. Okay. I don't think that people understood him at that time. So here I say, let us add infinities to quadratic equation. And this is one of the ways to add infinities to quadratic equation. Mm-hmm. This is quadratic equation. It is this diagram. So what we call quadratic equation is when c goes to infinity and we, okay. Let me put here c squared.
Ah, okay.
So I take this c to infinity, this c to infinity. It is quadratic equation.
Yes.
You see, everything is determined by its by degree. Quadratic equation means that you cover y 2 times. No, you cover x 2 times, you cover y 1 time. Mm-hmm. You see, you intersect this line once. You intersect this line twice. So what else could you write? If you intersect the bottom line twice, you have to intersect the upper line twice, because the number of preimages of 0 should be equal to the number of preimages of infinity, since they are homotopically equivalent, right? So you should have 2 points here, 2 points here. 1 point here, 1 point here. So this should be taught at schools. Come on. That quadratic equation is the degeneration of the following picture. Okay, let us take Desargues. So he made a lot of military contributions, okay? Because he designed the dam at La Rochelle. Okay? So this is, sorry. So this is quadratic equation. If you forgot how quadratic equation looks like, it looks like this. Okay? Projective quadratic equation. In general position. Quadratic means 2 points here, 2 points here. That y equals to quadratic means 1 point at 0 and 1 point at infinity. Okay? And all the rest are the generations of this picture. So actually, quadratic equation has 5 parameters. So once again, this 0, 2 came from these 2 0 1s coming together. You see, people study this quadratic function in the middle school, okay? If somebody will tell them that quadratic equation is something like this, and it is the only way to study quadratic equation, to study these pictures, they will not let neither me nor my child to enter the school. This is quadratic equation, okay? Okay, so this nice thing as quadratic equation is also interesting because, look, this is a Feynman diagram. The way to see this Feynman diagram is as follows. Something goes from the bottom line, something goes from the vertical line. They interact, bam, the momenta join together. They interact again, bam, we go vertical. Then they emit vertical momenta. Hooray, another vertical momenta emitted, hooray, then you go horizontally. Okay? Okay. Now, what should we describe here? We should describe here 2 things. First thing is the fate of the particle. Okay? So particle is something that is flying here, and that could be hit from blue lines. You see? You see, now I'll write the particle as a thick line. So now this is a particle. This is a particle. Okay? When I write it this way, I see a particle that is hit by something external. Okay? So it is a picture 1. What happened? Particle hit by something external. Later on, I'll try to explain you that this is non-democratic picture. Egoist picture. But you see, before we go to democratic or universal picture, we should start with the egoist picture. You see, it's like when child is born. So first child understands who he is. And he is very different from the rest of the people. Later he understands that he is like other people. So I know it. Okay? So let us start with the picture number 1. I specifically write it picture number 1 because later there will be picture number 2. Okay? So in picture number 1, we have a particle that could be in the state given by an integer vector. And let us call this integer vector n. and this is the state of the particle. By the way, particle could also be somewhere in the space. So it's also a function of R. Of course, R is tropical. So this is the wave function of a particle. Okay? N1 times f of R plus N2 F2 of R, or in other terms, particles are sum over n Fn. Okay? So let us take this n basis and study the particle that has momenta n. Okay? N is not only momenta. It is a wrapping. It means that above the particle that has momenta n, there is an angle. And this angle wraps the phase in a way proportional to n. You see? I propose you to see this picture. So let us see. What is the Hamiltonian? You see, if you have a particle, it moves.
Where does R live?
So now I consider what happens. So in this model, R lives on CP1 times CP1 tropical. On the square.
Mm-hmm.
So Hamiltonian is the following. Let us write down the equation of motion, how particle moves. It's a trajectory of r dot equals to n. So this is trajectory of the particle in the state n. So what does it mean? It means that the Hamiltonian equals to Lie derivative n times d over dr. Okay? Or I can write it down as na d over dra. Lie derivative. So it is simple. So we exactly see what is going on. So if you are in the state with a given momenta, you move along this momentum. No, it's simple. However, the particle could change its momentum. So let me call this free. So would there be nothing that is coming from the outside? Particle would keep its momentum forever. But sometimes it gets hits from the outside. So how do we interpret it? Of course, we interpret this as an interaction. Okay? What does interaction do? It changes momenta. Okay? So here particle had momenta that was horizontal. Here is the interaction that hit it. And then particle goes this way. Here, similar thing happens. So let us see. What is the interaction? These blue lines emits elementary momenta delta. And these elementary momenta delta are hitting. The vertical line also emits momenta. And as you see, vertical line emits elementary momenta minus delta. If I change the direction, you see that it emits elementary momenta minus delta. Okay? And here these deltas are vertical. So, but this is because we had a quadratic line. So would we have not a quadratic line? Would we have more complicated line? There would be also lines coming from vertical things. Okay? So let me write more general picture. Here I could get a momenta. So this is delta 1. Here I could get a momenta and go this way. It will be delta 2. So in this picture, I have a particle that is bombarded by external momenta delta 1 and delta 2. In the result of this interaction, n goes to n plus delta. Okay? So this is interaction V delta. So what happens with the Hamiltonian of the particle? Hamiltonian of the particle is free Hamiltonian plus sum of delta fundamental. And here we have this V delta, where V delta acts as a shift. Okay? And when we put a particle here, we will get exactly this. So everybody who was studying quantum mechanics knows that when Hamiltonian is H3 plus U, okay, the evolution is given by free evolution plus hit by U, free evolution, another hit by U, etc. I explained this formula several times. when I described the very general solution of quantum mechanics. I always told that it is a formula that all physicists know and that no mathematicians know. And the difference between physicists and mathematicians is if you understand how to write perturbation theory for e to the th. So all physicists know this. So here I am applying this to this model. H3 plus interaction. And interaction changes momentum. So people, once again, people who studied, say, quantum electrodynamics or scattering theory maybe remember this picture. Electron or something is scattering on the kernel, on the nuclei, not on the kernel, on the nuclei. Nucleon, so it's electron. This is, say, proton, very heavy, or the nuclei of some element. And the electron is hit by what people are calling virtual photons. And this is the process of scattering. So if you never saw this picture, you can imagine. So that's how people from elementary particle physics explain the scattering on the Coulomb field of something that is very heavy and just doesn't feel that the electron is moving. Yeah, so it's exactly what happens here. This blue line is so heavy that it could emit any number of these deltas, and it would stay the same. The particle would absorb all these deltas and go further. Okay? It is a picture. You see, I am here not to give you definitions. I can give it, but it will not teach you. I am here trying to transfer my intuition. It's not my intuition, it's intuition of high energy physics. Okay? And of course, so that's it. Hamiltonian is given. What else do I need? Plus this sum of V delta. And do you know what I'm going to do right now? Let me surprise you, okay? I will surprise you because now I will do tropical mirror. I hope that you remember that this number n, this vector n, was a winding. It was a winding. Let me recall that the holomorphic map was actually R equals n times t. Phi equals n times phi. R plus I phi equals n I plus I phi. So this is a holomorphic map. Okay. Here is an example, C star to C star to the power n. So this process is as follows. Here I have a map C star to the power n. In this example, n equals to 2. And here I have this interaction. So now I'm talking about free motion. It's like this. So when I fix time, what is this n? It is the topological type of the wrapping of this string over phi angles of the target space. And if I have this wrapping, then I evaluate accordingly. So that's why this n is a wrapping. So for a moment, so we start with n being a wrapping. Hamiltonian is proportional to this n. Now, what is mirror? Mirror is the change of wrapping to what? Pasha, are you here?
I am here, but I don't know.
So what is mirror? You change the wrapping that we discussed by momentum.
Mm-hmm.
Hmm? But the equation, of course, is momenta where? Momenta in the dual circle. Okay? So it means that is, instead of writing things in terms of wrapping phi, I should go to the dual circle. Okay, I'll erase this. Dual circle. So n was wrapping. And now I want to understand it as a momenta. It means that now I say that state n is what? Is e to the I n and the dual thing I call y. Why not? It is this. I put the vector in the opposite direction to show that it's dual. Okay, Pasha, I see that you don't like it.
No. Everything good.
I put this canonical map. I like it better. Okay, so now I understand n this way. Now, what is this Hamiltonian that made me this motion? Okay, NA, of course, becomes d over ya. Okay, all right. And Hamiltonian and free Hamiltonian becomes d over dya, d over dra. So we see something interesting. Here Hamiltonian was the first order operator. That was corresponding to Lie derivative. that we know. And we were tracing it here. Now Hamiltonian is a second order operator. Of course, when this thing is applied to this function, it's the same. But when it is applied to the full Hilbert space, it's different.
So in this language, the change we are doing is like change of polarization in quantum mechanics, or P to Q.
You may say it this way. You see, of course, it's the same space.
Mm-hmm.
Okay, now we are coming to these mysterious operators, V. Could you guess what happens with these mysterious operators? How can we write it down in this representation? So you see here, we see hit, and we change. Hit, and we change. What actually happens? So what is V?
An exponent of y.
Great, Pasha, exactly. Thank you. Thank you for following the idea. Okay. Now, instead of having this crazy operators, we have exactly exponents of y. However, it is not the full truth. And of course, here we have some. It's not the full truth because actually there is something else that is standing here. But basically, idea is like this. And in order to get it properly, so please see what we have here. Okay. We have Laplacian plus potential. There will be something standing here, and we will come to it at a moment. But we have this Hori-Vafa, maybe given time Hori-Vafa, exponential deformation. Okay. So let me put it this way. My time is almost over. I explain the main thing that stands here. I'll explain later what would happen with this pre-exponent. Okay. And also, I was never talking about fermions, so there are several questions left. Open questions. What about fermions? Because when we studied the thing called Lie derivative, yes, remember, Lie derivative acted not on the space of functions, but actually on the space of differential forms. We ignored it for a moment, but we did it on purpose. We did it in order to feel what comes out. Okay. There was also an issue. saying that we need to keep track of the intersection numbers. So there is something about phi dynamics that was also forgotten here, you see. It is just description of this R picture, okay? So first question was what about fermions? But there is a second question. I don't have enough time. It's a question, issue of democracy, okay? It was called picture 1. Let me tell you what is the picture 2. Before I'll tell you what is the picture 2, I will tell you a sad story of marriage and divorce, okay? You see, I divorced, so I know it, okay? Those who never divorced could see it from the Feynman diagram, okay? So, from the point of view of the rest of the world, two people are coming together, then they are family, then they separate, right? Okay. However, imagine that you are one of these people, say this one. So what is your history? You live a long time being free, okay? Then you marry, and you are in a different state, okay? Then it happens that you divorce. I do not recommend, but it happens. And then you are free again. So this is your picture. For you, this is your trajectory. And these things are places where you have an interaction. But this is not a democratic way to see what's going on. Another way to see it is from your spouse point of view. He or she was free. Then, okay, since I'm a man, now I'll write the female point of view. She was free. Then she interacted with you. And then she left you. Okay? You just disappeared from her life. Okay? So I call this as general relativity for the family, for the people's relations. Okay? What you feel as an interaction, so you feel your partner as an interaction, she feels you as an interaction. And democratic way tells you that it is just what happens in the world. You see? So here I wrote you a tree, okay? Whereas this fat particle, you see I am fat, could be my word line. However, it's possible to write another picture, like this. So maybe the best way to depict it is to go to the simplest possible diagram, like here. So this is the linear equation. You see, Pasha criticized me for quadratic equation, so this is a linear equation. Y equal z minus a, or x minus a, x minus b times c. Pasha, do you see that this is a linear equation? Okay?
Yes. Yes.
Okay. So this is a linear equation. So there are many ways to interpret this linear equation. It's one way. you have this line and interaction. Okay. Say it's a male way.
No, but again, by linear, you mean that you can take a limit in which it becomes linear.
Of course. Linear projective. So these are, you see.
Okay, no,
We should prove
in
this.
that sense, I understand.
So this is, say, the male way, this is a female way, and there is also a crazy way. Okay. So there are many ways in which you interpret it as a trajectory of a particle with interactions. And all of these ways are compatible. Okay? So, let me come to my favorite picture from the high energy physics. So this is a nuclei, and this is an electron. You know that it is nuclei because it's fixed, but you can distinguish electron from photon. That is here. This is virtual. This is real. You see. Here, there is a democracy. Namely, you can take any way to make a tree so it's a tree, of course. You can pick up 2 points and the rest you consider as branches. Okay? So whenever you have a tree, you can say this is beginning, this is the end, and the rest are branches. Okay? So there are many ways to do this. And if you interpret it in this way, you are choosing only one particular way. So the proper way to describe holomorphic curves is, of course, not from the point of view of the distinguished particle with interaction. There is a democracy. And in order to generate this democracy, you are doing not a particle theory, you are doing quantum field theory, where what you call interaction and what you call the free particle are equivalent. Unfortunately now, I have no more time to go into details. I hope I puzzled you a bit. Pasha, have I puzzled you?
Yes, you exactly. You came to the point which I wanted to hear.
Ah,
But yes, now we have to stop.
yes. So then I wanted to discuss it tomorrow. But Pasha,
Yes.
since you are not going tomorrow,
No.
okay, then I will not discuss it tomorrow.
No.
I will discuss it. I will, because it's a place where you need to ask questions, and that's why I need interaction. So I will move it to Wednesday. Okay.
I could watch in the recording, but I cannot retroactively ask questions.
Yes, but I need you to ask questions interactively.
Mm-hmm.
That's why. You see, I put some questions, you see, about fermions, about how this particle with interactions is equivalent to field theory where we have democracy. So I want you to think about it. Because if I give you answers while you are not thinking about it, not suffering, you see, you will not understand my answers. Okay? Maybe it's a way how I should go, yes? Puzzle at one talk and give answers on the second. Okay. Okay. So this particle with interactions or field theory, why it is the same? How could it be that it is the same? And why this is actually the content of the BCOV action? And where is BCOV action here?
This is very perplexing. BCOV is very specific to the dimension.
Ah, you see, this is completely wrong.
Mm.
What about fermions? Then particle versus field theory, QFT. And third, where is BCOV? And this I will explain on the next talk. So, at least Pasha, did you get the equations? Did you get the puzzles here?
Yes,
Huh?
although actually I don't understand question one. I understand the other questions, but question one.
What about fermions?
Mhm.
Okay. Question one was, so while I was writing it like this, I was thinking that I go this way, that things are like this. So it is Lie derivative, yes?
Mhm.
But Lie derivative should act, we forgot, that Lie derivative should act on the space of differential form.
Ah, okay, sure.
So you see, we forgot, here we see only functions. Where are differential forms? But since it's expected to be intersection theory, after all, yes, we should keep in mind differential forms. And
Yes.
the question would be, what are differential forms entropically? You see, we moved to the curve so quick. We thought that we understood everything. No, we understood almost everything. We understood the bosonic piece of the theory. Okay. We got this, and now this looks like Laplacian. However, as you know, Laplacian has fermionic part. Where is it? Where are fermions here?
Mhm.
This is bosonic piece of the story. There should be fermions. Okay?
Right.
There should be intersection theory. Do you see? It's equation number one.
Yes.
Section number two is about democracy. Me and my former spouse should be treated simultaneously. What does it mean?
No, that's clear. Yes.
No, it's not clear. You see, for a person, it's hard to think in this way. For the theory, it's as difficult as this.
No, I think it's very clear. I mean, you're starting with drawing kind of graphs in your tropical CP2, sorry, CP1 cross CP1, and then you start with putting additional structure in them, and the structure is completely superfluous.
Ah, okay, I see. But then you need to write down the interaction.
Mhm.
Okay, so this would be particle versus CFT. And the third question is how this is related to BCOV. And here the answer would be, okay, Witten, Gerasimov, Barannikov, Kontsevich, deformation of complex structures. And BCOV is just one example. And this is another example that is much better than BCOV, because here everything is explicit. In BCOV, it's very hard to compute. You need to pick up Calabi-Yau manifold. You cannot compute on Calabi-Yau manifold anything. Yes? You need to write down some propagators. How can you get these propagators on Calabi-Yau manifold if you have no Calabi-Yau manifold in your disposal? Okay? So you are doing just existence theorems. However, here everything is explicit. Here all Feynman diagrams are clear and seen. All problems are combinatorics. Okay? That's why this is much, much better than original BCOV. However, they belong to the same family. And the reason why this is better is because when you speak about phenomena, zeros cohomology are much better than first cohomology. So functions are simpler than vector fields, okay? And vector fields are simpler than bivector fields. Also, functions with values and functions are simpler than vector fields with value in 0, 1 forms, okay? So symmetries are simpler than abstractions, okay? Okay, I'm talking philosophy, but here I'll try to explain it. And that is the reason why here everything is simple, doable, computable. Computer, you can find something, okay? Okay, this is, Pasha, as you say, this is one line explanation. During the next talk, I'll explain this in more detail. Why this is the BCOV, but the easier case, okay? So you see, this is linear function. That is a bit more singular than your teachers think, yes? And this is BCOV. That is a bit simpler than people think, okay? That's it. See you next time.
Thank you. Thank you very much. Thank you.
You're welcome. So now I hope that everybody from China would, and from Asia.
Okay.
So Pasha, could you please stop the recording?